Construction projects shape the physical world around us. They define skylines, connect cities, enable commerce, and support everyday life. From residential buildings to transportation infrastructure, from hospitals to manufacturing facilities, construction is one of the most capital-intensive and complex industries in the global economy. Yet despite decades of experience, advanced engineering software, financial oversight mechanisms, and highly trained professionals, one persistent pattern continues to repeat itself. Projects exceed budgets. They overrun initial cost estimates. They expand beyond financial expectations. And when they do, the explanation is often simplified. People say the project was mismanaged. They say the contractor underperformed. They say the market shifted unexpectedly. They say mistakes were made. But the reality is far more complex. Cost overruns are rarely the result of a single catastrophic error. They are rarely caused by one irresponsible decision. Instead, they are the predictable outcome of layered systems interacting under uncertainty. Construction is not a linear process. It is a network of interdependent decisions, evolving information, financial assumptions, regulatory requirements, human behaviors, and market forces. Each of these components carries variability. And when variability accumulates across multiple dimensions, financial deviation becomes increasingly probable. To understand why construction projects go over budget, we must look deeper than surface-level explanations. We must examine how budgets are formed, how assumptions are embedded, how expectations are anchored, how scope evolves, how risk compounds, how productivity shifts, how contracts influence behavior, how supply chains introduce fragility, how leadership culture affects transparency, and how small inefficiencies, when left unmanaged, grow into measurable financial consequences. This is not a documentary. This is an educational masterclass. Construction projects shape the physical world around us. They define skylines, connect cities, enable commerce, and support everyday life. From residential buildings to transportation infrastructure, from hospitals to manufacturing facilities, construction is one of the most capital-intensive and complex industries in the global economy. Yet despite decades of experience, advanced engineering software, financial oversight mechanisms, and highly trained professionals, one persistent pattern continues to repeat itself. Projects exceed budgets. They overrun initial cost estimates. They expand beyond financial expectations. And when they do, the explanation is often simplified. People say the project was mismanaged. They say the contractor underperformed. They say the market shifted unexpectedly. They say mistakes were made. But the reality is far more complex. Cost overruns are rarely the result of a single catastrophic error. They are rarely caused by one irresponsible decision. Instead, they are the predictable outcome of layered systems interacting under uncertainty. Construction is not a linear process. It is a network of interdependent decisions, evolving information, financial assumptions, regulatory requirements, human behaviors, and market forces. Each of these components carries variability. And when variability accumulates across multiple dimensions, financial deviation becomes increasingly probable. To understand why construction projects go over budget, we must look deeper than surface-level explanations. We must examine how budgets are formed, how assumptions are embedded, how expectations are anchored, how scope evolves, how risk compounds, how productivity shifts, how contracts influence behavior, how supply chains introduce fragility, How leadership culture affects transparency. And how small inefficiencies, when left unmanaged, grow into measurable financial consequences. This is not a documentary. This is an educational masterclass. Chapter 1: Foundations of Budget Formation. Every construction project begins with a financial forecast. This forecast is often presented as a budget. It appears structured, organized, detailed, and precise. Line items are categorized. Quantities are calculated. Unit rates are applied. Contingencies may be included. At first glance, the document appears definitive. But what many stakeholders fail to fully appreciate is this. A budget is not a fact. It is a prediction. And predictions depend on information. At the earliest stages of a project, information is incomplete. Architectural drawings may be conceptual. Engineering calculations may still be preliminary. Geotechnical data may be limited to initial sampling. Material specifications may not yet be finalized. Supplier engagement may not have begun. Despite this, investment decisions are often required. Land must be acquired. Financing must be secured. Public announcements may be made. Board approvals must be obtained. This creates a structural tension. Financial commitment precedes technical certainty. The earlier the budget is formed, the wider the uncertainty range becomes. In project management theory, this relationship is well understood. Cost accuracy improves as design maturity increases. At conceptual design stage, cost estimates may vary significantly. At detailed design stage, estimates become more precise. However, the paradox is this. The ability to influence cost is highest early in the project. But cost certainty is lowest at that same moment. This creates a decision environment in which major financial commitments are made under conditions of limited clarity. To compensate, estimators rely on historical data. They reference similar projects completed in the past. They apply benchmark cost per square meter. They adjust for inflation. They include allowances for known unknowns. But history is not identical to the future. Market conditions evolve. Regulations change. Design standards advance. Labor availability fluctuates. And no two sites are ever truly identical. Each project contains unique variables. So while benchmarking provides guidance, it cannot eliminate uncertainty. Another foundational issue lies in how single-point estimates are communicated. When a budget is presented as one number, it creates psychological anchoring. Even if internally understood as a range, externally it often becomes a commitment. Once stakeholders internalize that number, deviation feels like failure. This anchoring effect influences future decisions. Design teams may subconsciously compress scope to fit within the anchor. Executives may resist acknowledging emerging risks. Procurement teams may delay escalation discussions. And this behavior delays adjustment. Delayed adjustment increases financial exposure. A more transparent approach would present budgets as ranges with defined confidence levels. For example, rather than stating the project will cost $50 million, a more realistic framing might communicate a range between $45 and $55 million depending on evolving design factors and market conditions. This communicates uncertainty explicitly. But in competitive markets, ranges are sometimes avoided. Investors prefer clarity. Clients prefer certainty. And organizations sometimes provide a single number to strengthen confidence. Ironically, this pursuit of certainty can weaken long-term financial control. Because reality will eventually reveal the uncertainty that was present from the beginning. There is another structural characteristic embedded in early budgets. Contingency. Contingency is intended to absorb unknown risks. It is a financial buffer. However, contingency is often misunderstood. Some stakeholders treat contingency as optional. Some treat it as excess. Some treat it as accessible for scope enhancement. But contingency is not surplus. It is protection. If contingency is reduced to make a project appear more affordable, financial resilience declines. And when inevitable adjustments occur, the project has limited capacity to absorb them. In addition, early budgets often assume productivity baselines that reflect optimal conditions. They assume smooth sequencing. They assume coordinated execution. They assume consistent workforce availability. But real-world conditions rarely align perfectly with assumptions. Weather interruptions occur. Inspections delay progress. Rework becomes necessary. Minor coordination errors create inefficiencies. If the baseline budget assumes ideal performance, deviation becomes likely. Another foundational factor is the compression of timelines. Aggressive schedules increase cost risk. When design is rushed to meet procurement milestones, errors are more likely. When procurement is rushed to secure pricing, supplier evaluation may be limited. When execution is rushed to meet public deadlines, overtime increases. And overtime amplifies cost. At the foundation stage of budgeting, time and cost are deeply interconnected. Shorter schedules reduce financing duration but increase execution intensity. Longer schedules reduce execution intensity but increase overhead and financing cost. Balancing these variables requires strategic modeling. Yet early budgets sometimes treat schedule as fixed rather than dynamic. This reduces flexibility. And reduced flexibility increases exposure. Ultimately, the foundation of budget formation is built on assumptions layered over incomplete information. This is not inherently flawed. It is unavoidable. But when assumptions are not explicitly identified and managed, they become hidden risk carriers. A professionally structured budget formation process should identify assumption dependencies, quantify uncertainty ranges, model scenario variations, maintain contingency discipline, communicate confidence levels clearly, and update forecasts continuously as information evolves. Without these practices, the budget becomes static while reality remains dynamic. And static numbers cannot accurately reflect dynamic systems. This is the first structural driver of cost overruns. Not incompetence. Not negligence. But the natural consequence of forming financial commitments before full information is available. Understanding this foundation changes how we interpret overruns. It shifts the narrative from blame to system design. Because when we recognize that early budgets are predictive models rather than fixed truths, we can design systems that adjust intelligently as knowledge increases. In the next chapter, we will examine how design maturity and information gaps evolve over time, and how those evolving details reshape cost expectations. Chapter 2: Design Maturity and Information Gaps. As a construction project moves forward, information gradually becomes more detailed. Lines on conceptual drawings become engineered dimensions. Preliminary layouts become coordinated systems. Assumptions begin to transform into specifications. But this transition from concept to detail is not smooth. It is layered. It is iterative. And it directly influences cost behavior. At the earliest stage of design, architectural intent defines space, function, and general configuration. Structural systems are proposed. Mechanical and electrical systems are outlined. However, many technical parameters remain undefined. Wall assemblies may not yet specify exact material thickness. Mechanical systems may not yet include finalized equipment capacities. Electrical distribution may not yet account for full load diversity. Site conditions may not yet reflect full geotechnical investigation. Despite these gaps, early budgets are often approved. This creates a dependency. Cost is estimated based on partial clarity. As design matures, clarity increases. But increased clarity rarely reduces cost. It typically refines it upward. When structural engineers perform deeper analysis, load paths may require reinforcement. When mechanical engineers finalize heating and cooling calculations, equipment sizing may increase. When regulatory compliance reviews occur, fire protection systems may expand. Each layer of refinement introduces precision. And precision has financial consequences. Design maturity operates on a curve. At 10% design completion, variability is extremely high. At 30%, variability narrows but remains significant. At 60%, most major systems are defined. At 90%, only minor detailing remains. However, major procurement decisions sometimes occur before 60% maturity. This timing gap introduces exposure. If procurement locks pricing before design stabilizes, change orders become likely. If design evolves after contracts are signed, financial renegotiation becomes necessary. This dynamic creates friction. Friction increases administrative cost. Administrative cost increases overall expenditure. Another issue emerges in interdisciplinary coordination. Modern construction involves multiple engineering disciplines working simultaneously. Architectural, structural, mechanical, electrical, plumbing, fire protection, civil engineering, specialized consultants. Each discipline produces drawings. But drawings do not exist in isolation. A structural beam may intersect a duct route. A plumbing stack may conflict with a shear wall. An electrical tray may overlap a mechanical support frame. These coordination conflicts are often identified through digital modeling tools. But they are not eliminated instantly. Resolving clashes requires redesign. Redesign requires time. Time influences cost. If coordination occurs late in the design process, procurement may already be underway. Materials may have been ordered. Fabrication may have begun. Late adjustments at this stage are expensive. Therefore, the timing of design maturity is critical. Early coordination reduces downstream correction cost. Late coordination amplifies it. There is also the matter of specification escalation. During early design, materials may be described generically. Concrete grade may be assumed at a standard strength. Finishes may be labeled as typical commercial quality. Equipment may be defined by performance range rather than brand. As stakeholders review designs, expectations can shift. Clients may request higher-end finishes. Sustainability standards may tighten. Energy efficiency targets may increase. Acoustic requirements may become stricter. Each upgrade enhances performance or appearance. But upgrades alter cost baselines. If these enhancements are not accompanied by budget recalibration, divergence grows. Another subtle factor in design maturity is regulatory interpretation. Building codes evolve. Local authorities may interpret requirements differently. Fire safety measures, accessibility compliance, environmental impact controls, and zoning conditions can introduce additional requirements. If regulatory clarity is obtained late, adjustments may cascade across multiple systems. For example, if fire compartmentation requirements increase, wall assemblies must be modified. Modified walls affect structural loads. Structural changes affect foundation sizing. Foundation adjustments affect excavation scope. And excavation adjustments influence schedule. One regulatory clarification can ripple across the entire cost structure. Design maturity is therefore not only about technical detail. It is about system stability. The more mature the design, the fewer unknown interactions remain. But achieving full maturity takes time. And time is often constrained by market pressure. Developers may rush design to secure financing. Public projects may accelerate timelines to meet political commitments. Private investors may push for rapid mobilization. Speed reduces design refinement opportunity. Reduced refinement increases downstream correction risk. This creates a paradox. The desire to save time early can create cost expansion later. A disciplined project environment recognizes this trade-off. It does not treat design as a formality. It treats design as risk reduction. The deeper the design clarity before execution, the lower the probability of disruptive change. However, no design can eliminate all uncertainty. Even at 100% documentation, field conditions can differ from expectations. Existing utilities may not be where maps indicate. Soil conditions may vary beyond sample locations. Weather events may alter sequencing assumptions. Therefore, design maturity reduces uncertainty but does not eliminate it. The key is alignment between design stage and financial commitment. If cost expectations are updated at each design milestone, alignment improves. If cost expectations remain fixed while design evolves, divergence accumulates. Professional cost control integrates estimating continuously with design progression. At 30% design, estimates are refreshed. At 60% design, estimates are refined. At 90% design, final adjustments are made. This iterative approach recognizes that information evolves. Static budgeting ignores that evolution. Another dimension to consider is value engineering. Value engineering is often introduced to reduce cost. But its timing determines its effectiveness. If value engineering occurs early, alternatives can be integrated smoothly. If it occurs late, redesign costs may offset savings. For example, changing a facade material at conceptual stage is relatively simple. Changing it after shop drawings are prepared is expensive. Timing again influences financial outcome. In many projects, value engineering becomes reactive rather than proactive. Cost overruns trigger reduction measures. But late-stage reductions rarely recover full deviation. They may compromise performance. They may introduce coordination risk. They may create tension between stakeholders. Design maturity, therefore, is not just a technical phase. It is a financial stabilizer. The more synchronized design progression and cost forecasting become, the stronger the budget foundation remains. When synchronization fails, overruns begin to form silently. Not because of incompetence, but because information moved while financial expectations stood still. Understanding this relationship between evolving information and static expectation is essential. Because it reveals that cost control is not about rigid enforcement. It is about adaptive alignment. In the next chapter, we will examine the psychological dimension of budgeting. How human perception and cognitive bias shape financial decisions long before construction begins. Chapter 3: Psychological Anchoring and Expectation Lock-in. Construction projects are technical systems. But they are also human systems. Behind every budget, every estimate, every contract, and every schedule, there are people making decisions. And human decision-making is not purely rational. It is influenced by perception. It is influenced by bias. It is influenced by cognitive shortcuts that evolved long before modern project management existed. To understand why construction projects go over budget, we must examine one of the most powerful psychological forces in financial forecasting: anchoring. Anchoring occurs when the first number introduced in a negotiation or evaluation becomes a reference point. Even if that number is uncertain, even if it is explicitly labeled as preliminary, it exerts influence. In construction, the initial budget becomes that anchor. When a project is announced at a certain cost, that number shapes every subsequent conversation. If the early estimate states that a development will cost $100 million, that figure becomes embedded in stakeholder expectation. Investors internalize it. Board members reference it. Public officials repeat it. Project managers build reporting frameworks around it. Even if the original estimate included uncertainty, the communicated number becomes fixed in perception. And once perception fixes, adjustment becomes difficult. If later design refinement indicates that the project will likely require $115 million, the reaction is not neutral. It is emotional. It feels like loss. It feels like failure. It feels like something went wrong. But in reality, the later estimate may simply reflect more complete information. The anchor created the illusion of precision. The revised number reveals underlying variability. This psychological dynamic affects behavior. Project teams may delay communicating emerging cost pressures. They may hope that future savings will offset increases. They may compress contingencies quietly. They may postpone difficult conversations. The longer adjustment is delayed, the larger the eventual correction becomes. This creates shock. And shock damages trust. Anchoring interacts with another cognitive force: optimism bias. Optimism bias is the tendency to believe that future outcomes will be more favorable than statistical evidence suggests. In construction, optimism bias manifests in schedule assumptions, productivity expectations, and risk assessment. Teams often assume that disruptions will be minor. They assume weather delays will be manageable. They assume suppliers will deliver on time. They assume regulatory approvals will proceed smoothly. While optimism fuels momentum, it can distort forecasting. If contingency is reduced because risks are believed to be unlikely, resilience declines. When risks eventually materialize, financial buffers are insufficient. Optimism bias is particularly strong in competitive bidding environments. Contractors seeking to win projects may understate costs to remain attractive. Developers seeking financing may present ambitious projections. Consultants may align estimates with client expectations to preserve relationships. These pressures are rarely unethical. They are structural. But structural pressure influences numbers. And numbers influenced by optimism often lack protective margin. There is also escalation of commitment. Once resources have been invested in planning and design, stakeholders become psychologically attached to the project vision. If costs begin to rise, abandoning or restructuring the project feels like loss of prior effort. As a result, decision-makers may continue committing funds rather than reassessing scope. This is not irrational. It is human. But in financial systems, emotional attachment can override objective recalibration. Another subtle factor is confirmation bias. When new information emerges, people tend to interpret it in ways that confirm existing beliefs. If a project team believes the budget remains achievable, early warning signs may be minimized. Small cost increases may be labeled temporary. Schedule slippage may be attributed to short-term disruption. The narrative remains optimistic until evidence becomes undeniable. By the time undeniable evidence emerges, corrective flexibility may be limited. Psychological forces also influence contingency management. When contingency exists, it can create a false sense of comfort. Teams may assume that any issue can be absorbed within contingency. But contingency is finite. If multiple minor issues consume it early, later major risks become exposed. There is also the phenomenon of social reinforcement. If senior leadership publicly commits to a number, subordinate managers may hesitate to challenge it. Organizational hierarchy can suppress dissent. Junior engineers may notice cost pressure. Procurement analysts may observe price escalation. But if the prevailing narrative remains stable, raising concerns may feel disruptive. Delayed reporting amplifies risk. Because early intervention is always less expensive than late correction. In large infrastructure projects, political visibility adds another layer of psychological pressure. Public announcements generate expectation. Media coverage reinforces financial commitments. Revising cost projections publicly can damage credibility. Therefore, organizations may resist updating numbers until absolutely necessary. This delay does not prevent cost increase. It only delays transparency. And delayed transparency increases the magnitude of adjustment required. To manage psychological drivers effectively, professional project environments implement structured reporting systems. Forecast updates occur at predefined intervals. Risk reviews are formalized. Independent cost audits may be conducted. Scenario modeling explores best-case and worst-case outcomes. By institutionalizing transparency, reliance on individual optimism decreases. Another effective strategy is probabilistic forecasting. Rather than presenting a single deterministic number, probabilistic models communicate likelihood distributions. For example, there may be a 50% probability the project completes within one range, and an 80% probability within a broader range. This reframes expectation. Instead of anchoring to a single figure, stakeholders understand variability explicitly. Language also matters. When communication emphasizes confidence levels rather than absolutes, psychological rigidity softens. Saying, based on current information, our most likely range is, creates flexibility. Saying, the project will cost, it creates anchoring. These differences may appear subtle. But in large-scale financial environments, subtle framing influences millions. Psychological forces do not operate independently from technical factors. They amplify them. Incomplete design creates uncertainty. Anchoring resists adjustment. Optimism underestimates risk. Escalation of commitment resists restructuring. Confirmation bias delays recognition. Together, these forces create expectation lock-in. Expectation lock-in is the condition in which stakeholders remain attached to an early financial figure despite evolving evidence. And when evidence eventually forces revision, the shift appears dramatic. But the shift was gradual all along. Professional financial discipline requires emotional discipline. It requires comfort with uncertainty. It requires courage to update forecasts early. It requires cultures that reward transparency rather than concealment. Construction cost overruns are therefore not only engineering challenges. They are behavioral challenges. Managing them requires understanding both numbers and human nature. In the next chapter, we move from psychology to structural mechanics. We will examine how scope expansion and design evolution systematically reshape cost, often without immediate visibility. Chapter 4: Scope Expansion and Design Evolution. At the beginning of every construction project, there is a defined scope. The scope describes what will be built. It defines the size, the function, the performance requirements, and the technical standards the finished asset must achieve. On paper, scope appears fixed. It appears documented. It appears controlled. But in reality, scope is dynamic. It evolves. And it evolves for reasons that are often rational, sometimes necessary, and occasionally unavoidable. Scope expansion is one of the most powerful structural drivers of cost overruns. Not because change is inherently negative, but because change interacts with contracts, schedules, procurement timing, and resource allocation in ways that magnify cost impact. To understand scope expansion, we must first understand what scope truly represents. Scope is not only physical dimensions. It includes quality expectations. It includes regulatory compliance. It includes performance thresholds. It includes aesthetic intent. It includes operational functionality. Each of these dimensions can shift during the life of a project. Consider a commercial office building. At conceptual stage, the scope may define a 10-story structure with standard office finishes. But as design progresses, stakeholders may refine expectations. 10 stories may become 12. Standard finishes may become premium finishes. Energy efficiency targets may increase to achieve sustainability certification. Acoustic performance may be enhanced to attract high-value tenants. Each refinement may appear incremental. Each may appear justifiable. But each adjustment modifies cost structure. And cost structure is sensitive to accumulation. Scope expansion rarely occurs in one dramatic event. It unfolds through sequences of small decisions. A client requests improved facade material. An operations team recommends enhanced HVAC redundancy. A regulatory authority mandates additional fire protection measures. An environmental review requires upgraded stormwater management. Each decision may improve the project. But improvements carry financial weight. The critical issue is not change itself. The critical issue is how change is integrated. If scope adjustments are identified early, evaluated transparently, and accompanied by budget recalibration, impact can be managed. If scope adjustments are introduced without structured cost analysis, divergence accelerates. There is also the phenomenon of scope creep. Scope creep differs from structured scope change. Structured scope change is documented, approved, and financially evaluated. Scope creep is informal. It emerges gradually without formal recognition. For example, during design coordination, a structural reinforcement may be added just to be safe. A finish may be upgraded because it appears minor relative to total budget. A feature may be included because it aligns with branding goals. Individually, these modifications may seem insignificant. But cost systems respond to aggregation. When 10 minor enhancements occur across different disciplines, cumulative impact becomes substantial. Another layer of complexity arises when scope change intersects with procurement timing. If materials have already been ordered, modifying specifications may trigger cancellation fees. If fabrication has begun, redesign may require scrapping partially completed components. If subcontractors have mobilized, schedule shifts may create idle labor. Late scope changes are exponentially more expensive than early changes. This is known as the cost of change curve. The earlier a change occurs, the lower its financial impact. The later it occurs, the greater its ripple effect. Yet in many projects, scope clarification continues deep into execution. This is often due to incomplete design maturity, evolving stakeholder expectations, or external pressures. Public infrastructure projects are particularly vulnerable. Community input may introduce new requirements. Political stakeholders may advocate for enhancements. Accessibility features may expand. Environmental mitigation measures may intensify. Each of these drivers can reshape project boundaries. And because public projects often operate under intense scrutiny, changes may be implemented rapidly without full financial modeling. Private developments face similar pressures. Market positioning may evolve. Tenant requirements may shift. Competitors may influence design differentiation. Developers may decide to upgrade finishes to attract premium occupants. Strategic adjustments are not inherently flawed. But if financial alignment does not accompany them, cost overruns become likely. Another subtle mechanism of scope expansion is interpretation drift. Even when scope is documented clearly, different parties may interpret requirements differently. An architect may envision a facade with precise detailing. A contractor may interpret drawings more generically. An engineer may specify tolerances conservatively. Discrepancies between interpretation and expectation can lead to rework or upgrade. Clarifying intent late in execution can generate claims and change orders. This introduces negotiation. Negotiation introduces delay. Delay introduces cost. Change orders are formal manifestations of scope evolution. They are contractual tools to adjust cost and schedule when scope changes. However, frequent change orders can destabilize financial predictability. Each change order requires evaluation, negotiation, documentation, and approval. Administrative overhead increases. Cash flow planning becomes more complex. If change orders accumulate beyond contingency capacity, financial stress intensifies. There is also the psychological element of incremental justification. When a project is already large, incremental additions may feel small relative to total scale. Adding 1% to a large budget can represent millions. But because it is framed as a percentage, it may feel manageable. Repeated small percentages, however, compound. 1% increases become 5%. On large infrastructure projects, 5% can represent enormous financial expansion. Scope expansion is also influenced by technological evolution. Over multi-year timelines, new materials and systems may become available. Teams may decide to integrate advanced technology, smart building systems, enhanced automation, higher efficiency equipment. While innovation improves long-term value, mid-project adoption disrupts cost stability. The tension between innovation and financial discipline must be managed deliberately. Another dimension is contractual clarity. If project scope is vaguely defined in early contracts, interpretation disputes become more likely. Ambiguity benefits no one in the long term. Clear scope definitions reduce downstream friction. Professional project governance includes strict change management processes. Every proposed change is documented. Its cost impact is quantified. Its schedule impact is modeled. Its risk implications are evaluated. Decision-makers review trade-offs consciously. Without such governance, scope evolves informally. And informal evolution rarely aligns with formal budgets. It is important to recognize that scope expansion is not always negative. Sometimes expanding scope enhances long-term value. Upgrading insulation may reduce operational energy cost. Improving structural resilience may extend building lifespan. Enhancing design quality may increase asset value. The issue is not whether scope changes. The issue is whether financial expectations adapt accordingly. Static budgets cannot absorb dynamic scope indefinitely. When scope expands and budget does not adjust proportionally, overrun becomes inevitable. Understanding scope expansion reframes cost overruns as structural phenomena. Projects do not exceed budgets simply because someone failed. They exceed budgets because scope evolved while financial anchoring remained rigid. The solution is not to eliminate change. The solution is disciplined integration. In the next chapter, we will examine how external market forces, particularly material price volatility and labor fluctuation, introduce additional layers of unpredictability into already complex financial systems. Chapter 5: Market Volatility and Price Drift. Construction projects do not operate in isolation. They exist within economic systems. And economic systems move. Material prices fluctuate. Labor markets tighten and loosen. Energy costs shift. Transportation networks experience disruption. Currency exchange rates vary. Interest rates rise and fall. These external variables operate independently of individual project planning. Yet they directly influence project cost. When a budget is formed, it reflects market conditions at a specific moment in time. Steel may be priced at one level. Concrete may be stable. Fuel may be predictable. Labor availability may appear sufficient. But construction projects often span multiple years. Over extended timelines, market stability is statistically unlikely. Even modest volatility can reshape cost assumptions. Consider structural steel. Steel prices are influenced by global demand, raw material extraction, trade policy, transportation cost, and geopolitical stability. If global demand increases due to infrastructure expansion in another region, supply tightens. When supply tightens, price rises. If a project locked its early estimate based on prior steel rates, upward price drift may emerge during procurement. Similarly, cement and concrete pricing can shift due to energy cost, environmental regulation, or regional production constraints. Mechanical equipment may be sourced internationally. Currency fluctuation can increase import cost. Electrical components may depend on semiconductor supply chains. Disruption in one manufacturing region can delay delivery worldwide. Labor markets introduce another dynamic layer. Construction labor is highly sensitive to regional economic cycles. When development activity increases rapidly, demand for skilled trades rises. If supply of skilled labor does not increase proportionally, wage rates escalate. Projects that assume stable labor costs may encounter upward pressure. In competitive labor environments, contractors may pay premiums to secure crews. Premium pay affects not only base wage but also overtime rates. If productivity decreases due to inexperienced substitute labor, financial impact multiplies. Market volatility also interacts with schedule. When material lead times extend unexpectedly, sequencing changes. Delayed delivery can idle crews. Idle crews reduce productivity. Reduced productivity increases cost per unit of output. Even if material price remains stable, delivery delay introduces financial inefficiency. Another factor is inflation. Inflation erodes purchasing power over time. In long-duration projects, inflation risk becomes substantial. If inflation assumptions in early budgeting were conservative, later procurement phases may exceed allowances. Financing cost is also influenced by macroeconomic conditions. Interest rates affect borrowing expense. If a project relies on debt financing, rising interest rates increase carrying cost. Extended schedules compound financing exposure. Thus, market volatility affects both direct construction cost and indirect financial structure. Some projects attempt to mitigate volatility through early procurement. Locking in material pricing through long-term supply contracts can reduce exposure. However, early procurement requires storage, insurance, and cash flow allocation. If design changes later, pre-purchase material may become obsolete. Risk shifts rather than disappears. Another mitigation strategy involves escalation clauses in contracts. Escalation clauses allow price adjustment if market indices move beyond defined thresholds. While this reduces contractor risk, it transfers exposure to owners. Contract structures determine how volatility risk is allocated. In fixed-price contracts, contractors absorb some volatility risk. In cost-plus contracts, owners retain greater exposure. Each structure carries trade-offs. Volatility also introduces forecasting difficulty. When markets are stable, estimates rely on recent pricing data. When markets are unstable, historical pricing becomes unreliable. Forecast confidence declines. In periods of rapid economic change, even short-term estimates become uncertain. Global events can amplify volatility. Pandemics disrupt supply chains. Trade disputes alter tariff structures. Natural disasters damage production facilities. Political instability restricts resource extraction. Construction markets are interconnected globally. A disruption in one region can propagate internationally. The key insight is this: market volatility is not an anomaly. It is normal. Financial systems must assume variability rather than stability. If early budgets assume constant pricing across multi-year timelines, they embed fragility. Professional cost planning integrates escalation modeling. Rather than assuming flat pricing, models incorporate projected inflation curves. Scenario analysis tests best-case and worst-case market conditions. Sensitivity analysis identifies which materials carry highest volatility exposure. For example, structural steel may represent a significant percentage of cost. If steel price increases by 10%, total project impact can be calculated. By identifying high-sensitivity components early, mitigation strategies can be prioritized. Another protective measure is diversification of suppliers. Relying on a single source increases exposure to disruption. Multiple sourcing reduces dependency risk. However, diversification may increase administrative complexity. Risk management always involves trade-offs. Some organizations use hedging instruments for commodities. While not universally applied in construction, financial hedging can stabilize cost exposure for certain materials. Such strategies require sophisticated financial oversight. The broader lesson remains consistent. External economic forces will move. Projects must be structured with flexibility. Static budgets in dynamic markets create tension. When tension accumulates without adjustment, overrun becomes visible. Market volatility alone may not cause catastrophic deviation. But when combined with evolving scope, psychological anchoring, incomplete design, and productivity variability, it compounds systemic risk. Cost overrun is rarely the product of one driver. It is the interaction of multiple drivers simultaneously. Understanding market volatility adds another layer to that system. In the next chapter, we move from external economic forces to internal execution forces. We will examine productivity drift, site efficiency, and how small operational inefficiencies quietly expand costs over time. Chapter 6: Productivity and Execution Friction. If budgets are formed on assumptions, and markets introduce volatility, execution introduces reality. Construction does not happen in spreadsheets. It happens on sites. On uneven ground. In changing weather. Through coordination between dozens of subcontractors. Through thousands of daily micro-decisions. And it is here, during execution, that productivity becomes one of the most underestimated drivers of cost overruns. Productivity is often defined simply as output per labor hour. But in construction, productivity is influenced by far more than worker effort. It depends on sequencing. It depends on coordination. It depends on clarity of drawings. It depends on material availability. It depends on site logistics. It depends on supervision quality. It depends on morale. It depends on environment. When early budgets are created, productivity assumptions are embedded. Estimators assume certain installation rates. They assume how many square meters can be completed per day. They assume how many meters of piping can be installed per crew per shift. These assumptions are often based on historical averages under stable conditions. But construction rarely occurs under perfectly stable conditions. Small disruptions occur daily. A delivery arrives late. An inspection is delayed. Weather interrupts concrete placement. A crane becomes temporarily unavailable. A drawing revision pauses work in one area. Individually, these disruptions may appear minor. But productivity is sensitive to interruption. When workflow is disrupted, crews lose rhythm. When crews lose rhythm, output declines. When output declines, labor hours increase. And labor hours directly influence cost. Even a 5% productivity loss sustained over months can produce substantial financial impact. If a project assumed installation of 100 units per day but consistently achieves 95, schedule pressure begins to accumulate. To recover schedule, management may authorize overtime. Overtime increases wage cost. Extended shifts reduce worker efficiency further. Fatigue increases error probability. Errors create rework. Rework consumes material and labor. And the cycle continues. Site congestion is another productivity factor. Large projects often involve multiple trades working simultaneously. If sequencing is not tightly coordinated, trades interfere with each other. Electricians wait for drywall completion. Mechanical installers wait for structural framing. Concrete crews wait for inspection approval. Waiting time is unproductive time. But it is paid time. Productivity modeling in early budgets rarely accounts fully for these friction layers. Budgets often assume optimized sequencing. Reality delivers imperfect synchronization. There is also the impact of workforce skill variation. In tight labor markets, contractors may hire less experienced workers to fill gaps. Less experienced workers may require more supervision. They may work slower. They may produce more errors. Error correction increases cost. If productivity assumptions were built around highly experienced crews, deviation becomes likely. Weather conditions further influence site performance. Extreme heat reduces safe working hours. Heavy rain disrupts earthwork. Cold temperatures delay curing processes. Wind halts crane operations. Weather variability is predictable statistically but unpredictable daily. Projects located in climates with seasonal extremes must incorporate buffer. If schedules ignore environmental variability, execution friction increases. Another dimension of productivity drift is equipment reliability. Heavy machinery requires maintenance. Unexpected breakdowns pause operations. If backup equipment is not available, downtime expands. Downtime extends schedule. Extended schedule increases overhead cost. Execution friction also emerges from communication gaps. If field teams receive unclear instructions, they may pause work for clarification. If design changes are not transmitted promptly, incorrect installation may occur. Correcting incorrect installation is expensive. Rework is one of the most costly forms of inefficiency in construction. It consumes labor twice. It consumes materials again. It delays subsequent activities. Quality control systems exist to reduce rework. But quality management requires discipline. If supervision is stretched thin, inspection may become reactive rather than proactive. Reactive correction costs more than preventive verification. There is also the phenomenon of acceleration. When a project falls behind schedule, management may accelerate activities. Acceleration often means adding crews. But adding crews in constrained spaces increases congestion. Congestion reduces productivity. So acceleration may increase costs without fully recovering time. Financial modeling must recognize that productivity is not linear. Doubling labor does not double output. Beyond certain thresholds, output per worker declines. This diminishing return is rarely reflected fully in early budgeting. Supply chain reliability also influences productivity. If materials arrive in the wrong sequence, crews cannot proceed efficiently. If components are missing, partial installation may occur, requiring return visits. Return visits increase handling cost. Handling cost increases labor consumption. Another subtle productivity factor is learning curve. At the beginning of a repetitive installation task, crews may work slower. As they gain familiarity, speed increases. But if scope changes disrupt repetition, learning benefits diminish. Frequent design revisions interrupt momentum. Interruption resets learning curve. Reset learning curve increases labor hours. Execution friction is cumulative. It rarely produces one dramatic spike. It produces steady drift. And steady drift is difficult to detect early. Financial reports may show marginal deviations. But over time, marginal deviations compound. Professional project control systems monitor productivity metrics continuously. Earned value analysis compares plan versus actual performance. Field reporting tracks output rates. Variance analysis identifies trends. Early detection allows corrective action. Late detection forces reactive spending. There is also cultural influence. If site culture encourages transparency, productivity challenges surface quickly. If site culture discourages reporting issues, friction remains hidden. Hidden friction grows. When finally acknowledged, recovery becomes more expensive. Execution is where planning meets complexity. Even well-designed budgets can unravel under sustained productivity drift. The lesson is not that productivity problems are avoidable entirely. The lesson is that they are inevitable to some degree. Financial resilience must assume some friction. Budgets that assume perfect efficiency create fragility. Budgets that include realistic productivity buffers create stability. Execution friction interacts with every previous driver. Incomplete design increases rework. Scope expansion increases sequencing disruption. Market volatility increases material delays. Psychological anchoring delays acknowledgement of drift. Together, they compound. In the next chapter, we will examine how risk mismanagement allows these small disruptions to accumulate into systemic financial exposure. Because risk is not only about rare catastrophic events. It is about frequent small events that interact over time. Chapter 7: Risk Mismanagement and the Compounding Effect. Every construction project carries risk. Risk is not optional. It is not a flaw in planning. It is a fundamental condition of building something that does not yet exist. Yet despite this reality, risk is often treated as a formality. A checklist. A document prepared during kickoff meetings. A register created to satisfy governance requirements. And then quietly forgotten. The most dangerous cost overruns do not come from one dramatic disaster. They come from unmanaged risk quietly compounding in the background. To understand this, we must redefine risk. Risk is not only catastrophic failure. Risk is uncertainty that affects objectives. Uncertainty in price. Uncertainty in productivity. Uncertainty in weather. Uncertainty in regulatory approval. Uncertainty in supply chain reliability. Uncertainty in labor availability. Every uncertainty carries probability. Every probability carries potential financial impact. When projects fail to quantify these properly, budgets become exposed. The first common failure in risk management is optimism bias. Teams identify risks, but they underestimate probability. They assign low likelihood to events they believe are manageable. They assign low impact to events they have not experienced recently. Human memory influences risk perception. If the last project did not experience severe weather delays, planners assume favorable conditions will continue. If material prices have been stable for years, escalation risk is minimized. This is not negligence. It is cognitive bias. The second failure is lack of contingency realism. Contingency is often misunderstood. It is not extra money for comfort. It is a calculated reserve designed to absorb uncertainty. Yet in competitive environments, contingency becomes politically sensitive. Owners may reduce contingency to lower headline budget. Contractors may minimize contingency to win bids. Executives may cut contingency to make financial metrics appear stronger. When contingency is reduced without reducing risk exposure, vulnerability increases. Risk does not disappear because it is removed from a spreadsheet. The third failure is treating risks independently. Construction risks rarely act alone. Material delay increases labor idle time. Labor idle time increases cost. Schedule delay increases financing cost. Financing cost increases total exposure. When one risk event triggers secondary effects, compounding begins. This compounding effect is rarely modeled accurately. Many risk registers assign isolated dollar values. But real projects experience cascading interaction. A regulatory delay pushes procurement into peak season. Peak season increases material prices. Higher material prices increase working capital requirements. Increased working capital strains cash flow. Cash flow strain increases borrowing. Borrowing increases interest cost. Interest cost reduces profit margin. One initial risk multiplies across the system. Another weakness in risk management is failure to update assumptions. Risk assessment is often conducted at project initiation. But construction environments change constantly. New information emerges. Market conditions shift. Subcontractor performance varies. If risk registers are not updated regularly, they become historical artifacts rather than decision tools. Professional project management integrates risk review into routine reporting cycles. Monthly risk workshops. Probability reassessments. Impact reevaluations. Trend analysis. This discipline transforms risk from static documentation into dynamic control. Another dimension of risk mismanagement is allocation confusion. In construction contracts, risks are allocated between parties. Some risks belong to the owner. Some belong to the contractor. Some are shared. But allocation on paper does not eliminate impact. If a contractor assumes risk for unforeseen ground conditions, they must price it properly. If they underprice that risk, margin erodes when conditions differ from assumptions. If the owner retains certain regulatory risks but fails to manage them proactively, delay still impacts overall schedule. Poorly defined risk allocation creates disputes. Disputes create legal cost. Legal cost consumes time and money. Disputes also reduce collaboration. Reduced collaboration increases friction. Friction increases inefficiency. Risk mismanagement also appears in procurement strategy. Long lead items carry high schedule sensitivity. If procurement schedules are not aligned with realistic production timelines, exposure increases. If supplier capacity constraints are ignored, delays multiply. In volatile markets, locking in prices early may reduce escalation risk. But early procurement increases storage cost. It increases cash flow demand. It increases risk of design changes requiring replacement. Risk decisions involve trade-offs. Sophisticated teams quantify these trade-offs. Reactive teams rely on instinct. Another underestimated risk factor is subcontractor financial stability. Construction ecosystems depend heavily on subcontractors. If a key subcontractor becomes insolvent mid-project, replacement costs rise. Schedule disruption occurs. Legal disputes follow. Financial vetting of partners is therefore part of risk management. But in aggressive bidding climates, lowest price often outweighs financial robustness. Short-term savings create long-term vulnerability. Whether risk deserves special attention. Many projects rely on historical averages to model weather impact. But climate variability is increasing. Storm frequency shifts. Temperature extremes become more common. Assumptions based on outdated historical data may underestimate exposure. Insurance can mitigate some impact. But deductibles, delays, and uninsured consequences remain. Force majeure clauses provide contractual relief. But relief does not eliminate financial strain. Risk mismanagement also includes communication failure. If early warning signs are ignored, risk escalates. For example, if productivity metrics decline gradually over several months, but leadership avoids confronting the issue to protect morale, corrective action is delayed. Delay magnifies impact. Timely transparency reduces compounding. There is also strategic risk. Market downturn during execution can affect demand forecasts. If a developer finances a project based on projected rental rates that later declined, revenue shortfall affects financial return. Budget overrun combined with revenue underperformance creates double exposure. Strategic risks are often considered external. But scenario planning can prepare organizations for volatility. One of the most powerful concepts in risk management is scenario simulation. Rather than relying on single-point estimates, advanced teams model multiple scenarios. Best case. Base case. Worst case. They assign probability distributions. They simulate thousands of outcomes. This approach reveals range, not illusion of certainty. When leadership sees potential downside clearly, decisions become more grounded. Risk culture determines effectiveness. If leadership punishes reporting of risks, teams hide issues. If leadership rewards transparency, risks surface early. Early surfacing reduces escalation. Risk management is not about eliminating uncertainty. It is about pricing it realistically. It is about preparing financially and operationally. It is about preventing small uncertainties from becoming structural crises. Cost overruns often appear sudden, but they are usually the final expression of compounded unmanaged risks. Each individual event may seem manageable, but unmanaged interaction creates exponential exposure. In the next chapter, we will explore how financial control systems, or the lack of them, either detect these compounding effects early or allow them to spiral beyond recovery. Because monitoring determines whether risk becomes manageable variance or catastrophic overrun. Chapter 8: Financial Control Systems and Budget Visibility. A project does not fail financially in one single day. It fails gradually, quietly, incrementally, and often invisibly. Until one day, the numbers become impossible to ignore. By the time leadership realizes the full scale of the overrun, options are limited. Margins are gone. Reserves are consumed. Relationships are strained. The difference between control variance and catastrophic overrun often comes down to one factor: financial visibility. Construction projects generate enormous volumes of financial data. Purchase orders, subcontract agreements, change orders, labor reports, equipment rentals, material invoices, forecast updates, cash flow schedules. The data exists, but data alone does not create control. Control requires structure. Control requires systems. Control requires discipline. The first major weakness in many projects is delayed cost reporting. If field costs are recorded weeks after they occur, leadership makes decisions based on outdated information. A project manager who sees last month's numbers cannot correct today's deviation. Timeliness is power. Lag is vulnerability. Professional project control systems operate on predictable reporting cycles. Weekly cost tracking. Monthly forecasting. Quarterly risk reviews. Each cycle answers a critical question. Are we still on track? But asking the question is not enough. The accuracy of the answer depends on forecasting methodology. Many teams rely on cost to date plus remaining budget. This approach assumes the remaining budget is still valid. But if productivity is declining, remaining budget may be unrealistic. A stronger method is estimate at completion. Estimate at completion asks, based on current performance, what will the final cost be? Not what we hoped. Not what we planned. But what reality now indicates. This requires continuous re-estimation. Re-estimation requires honesty. And honesty requires culture. One of the most dangerous financial behaviors in construction is hope-based forecasting. This occurs when teams believe performance will improve later without structural evidence. Perhaps they assume productivity will increase next month. Perhaps they believe weather will stabilize. Perhaps they expect material prices to normalize. Hope is not a financial control strategy. When forecasts are adjusted only after deviations become undeniable, the project loses time to react. Early forecasting allows early correction. Late forecasting forces damage control. Another weakness is cost code granularity. If expenses are grouped too broadly, visibility decreases. For example, if all mechanical work is recorded under one cost code, productivity variance in specific sub-activities may remain hidden. But if piping, ductwork, equipment installation, and testing are tracked separately, emerging inefficiencies become visible earlier. Granularity increases diagnostic precision. Precision enables targeted intervention. Cash flow forecasting is another critical dimension. Even profitable projects can fail if cash flow is mismanaged. Construction requires significant upfront expenditure. Labor is paid weekly. Suppliers demand payment. Subcontractors require progress payments. But client payments may lag. If payment terms are not aligned with cost outflow, working capital strain emerges. Working capital strain increases borrowing. Borrowing increases interest cost. Interest cost erodes margin. Cash flow visibility is therefore as important as cost tracking. Earned value management provides another powerful control mechanism. Earned value compares three metrics: planned value, actual cost, earned value. Planned value represents what should have been completed. Actual cost represents what has been spent. Earned value represents the budgeted cost of completed work. If actual cost exceeds earned value, cost overrun exists. If earned value lacks planned value, schedule delay exists. This framework transforms progress from subjective assessment into measurable performance. But earned value requires accurate measurement of completion percentages. Overestimating completion artificially improves reported performance. Accurate reporting requires field validation. Financial control also requires integration between departments. Estimating, procurement, site management, accounting, executive leadership. If these functions operate in isolation, financial blind spots appear. For example, procurement may secure material at a price higher than estimated. If that information is not immediately reflected in forecast, variance accumulates silently. Technology plays an increasing role in financial control. Modern project management software integrates cost tracking, scheduling, procurement, and reporting. Real-time dashboards provide visibility across stakeholders. But technology is only as strong as data input discipline. If field teams delay data entry, system accuracy declines. Automation reduces manual error. But governance ensures reliability. Another critical element is change management tracking. Every approved change order alters the financial baseline. If change orders are not recorded promptly and incorporated into forecasts, cost comparisons become misleading. Change order logs must be reconciled regularly. Disputed changes create further complexity. If work proceeds before pricing is finalized, exposure increases. Strong financial control systems monitor pending change exposure. They quantify potential impact before formal approval. This prevents surprises at project closeout. Audit culture is also essential. Periodic internal audits review compliance with cost procedures. Are purchase orders properly authorized? Are subcontract payments aligned with progress? Are contingency funds tracked separately? Audit does not imply distrust. It reinforces discipline. Human psychology again plays a role. Teams may delay reporting negative variance out of fear. Fear of criticism. Fear of reputational damage. Fear of losing bonus eligibility. But delayed transparency increases long-term consequence. Organizations that separate performance accountability from honest reporting achieve stronger control. Financial control is not about blame. It is about correction. Another underestimated risk is data overload without insight. Large projects produce thousands of cost line items. If reporting focuses only on total cost, early warning signals hide in detail. If reporting focuses only on detail, strategic overview may be lost. Balanced reporting requires both macro and micro perspective. Executive dashboards highlight overall variance. Detailed reports identify root causes. Forecast confidence levels should also be communicated. Not all forecasts carry equal certainty. Early in a project, uncertainty range is wider. As execution progresses, range narrows. Transparent communication of forecast confidence builds trust with stakeholders. It prevents shock at later stages. Ultimately, financial control systems function as early detection mechanisms. They do not eliminate risk. They do not eliminate market volatility. They do not eliminate design change. But they reveal deviation before it becomes irreversible. Cost overruns are rarely caused by one uncontrollable force. They are often amplified by delayed visibility. If deviation is identified when it represents 1% of budget, corrective action may be modest. If deviation is identified when it represents 15% of budget, options become limited. Financial visibility buys time. And time is leverage. In the next chapter, we will examine how leadership behavior and decision-making culture influence whether financial control systems are contingency funds tracked separately? Audit does not imply distrust. It reinforces discipline. Human psychology again plays a role. Teams may delay reporting negative variance out of fear. Fear of criticism. Fear of reputational damage. Fear of losing bonus eligibility. But delayed transparency increases long-term consequence. Organizations that separate performance accountability from honest reporting achieve stronger control. Financial control is not about blame. It is about correction. Another underestimated risk is data overload without insight. Large projects produce thousands of cost line items. If reporting focuses only on total cost, early warning signals hide in detail. If reporting focuses only on detail, strategic overview may be lost. Balanced reporting requires both macro and micro perspective. Executive dashboards highlight overall variance. Detailed reports identify root causes. Forecast confidence levels should also be communicated. Not all forecasts carry equal certainty. Early in a project, uncertainty range is wider. As execution progresses, range narrows. Transparent communication of forecast confidence builds trust with stakeholders. It prevents shock at later stages. Ultimately, financial control systems function as early detection mechanisms. They do not eliminate risk. They do not eliminate market volatility. They do not eliminate design change. But they reveal deviation before it becomes irreversible. Cost overruns are rarely caused by one uncontrollable force. They are often amplified by delayed visibility. If deviation is identified when it represents 1% of budget, corrective action may be modest. If deviation is identified when it represents 15% of budget, options become limited. Financial visibility buys time. And time is leverage. In the next chapter, we will examine how leadership behavior and decision-making culture influence whether financial control systems are used effectively or ignored until it is too late. Because even the best systems fail under poor leadership discipline. Chapter 9: Leadership Decisions and Organizational Culture. Construction projects do not overrun budgets because spreadsheets fail. They overrun because decisions fail. And decisions are made by people. Leadership is the invisible force behind every financial outcome. Two projects may face identical market conditions, similar labor challenges, and comparable design complexity. One finishes close to budget. The other collapses into overrun. The difference often lies in leadership behavior. Leadership determines how early warnings are handled. Leadership determines whether bad news is surfaced or buried. Leadership determines whether optimism overrides data. Leadership determines whether discipline is sustained or relaxed. The first leadership failure that drives overruns is denial. When early indicators show productivity decline or cost variance, leaders may dismiss them as temporary fluctuations. They may say, "It will stabilize next month." They may say, "This is normal at this stage." They may delay intervention to avoid disrupting momentum. But denial delays correction. And delay increases cost. Strong leadership responds to small variance early. Not with panic, but with investigation. The second leadership issue is misaligned incentives. If project managers are rewarded primarily for winning bids, they may underprice risk. If bonuses depend on maintaining the appearance of being on budget, they may delay reporting negative trends. If executives focus only on short-term quarterly metrics, long-term financial resilience suffers. Incentives shape behavior. Behavior shapes financial outcomes. Another leadership challenge is fragmented accountability. On complex projects, responsibility is distributed across multiple managers. Engineering, procurement, construction, finance. If accountability for overall cost control is unclear, problems fall between departments. Clear ownership creates clarity. Clarity accelerates response. Ambiguity creates drift. Communication style also matters. Leaders who create psychological safety encourage transparency. When team members feel safe reporting issues early, risks are surfaced quickly. When leaders react with anger or blame, teams conceal problems. Concealed problems compound. A culture of blame increases financial risk. A culture of accountability reduces it. Strategic decision-making under pressure is another critical factor. When a project falls behind schedule, leaders face difficult choices. Accelerate with additional crews. Resequence activities. Negotiate scope reduction. Inject additional contingency. Each option carries financial consequences. Poor decisions made under emotional pressure often amplify exposure. Effective leaders rely on data. They seek scenario analysis. They assess long-term impact before reacting. Short-term reaction without strategic evaluation often worsens position. Another dimension is experience. Leaders who have experienced previous overruns recognize early warning patterns. They understand that minor variance can escalate. They respect risk signals. Less experienced leaders may underestimate early deviation. They may lack pattern recognition. Mentorship and institutional knowledge transfer are therefore valuable. Organizational learning reduces repeated mistakes. There is also the issue of executive interference. In some organizations, executives override project-level risk recommendations to protect image or meet external commitments. For example, a project team may recommend increasing contingency due to market volatility. Senior leadership may reject the recommendation to maintain investor confidence. Short-term optics replace long-term realism. When volatility materializes, exposure becomes unavoidable. Transparent communication with stakeholders is a leadership strength. Hiding realistic projections to avoid discomfort often backfires. Trust once lost is difficult to regain. Another leadership failure is decision paralysis. Some leaders delay action, requesting additional analysis repeatedly. While analysis is valuable, excessive delay allows variance to grow. Decisive but informed action prevents escalation. Balance between speed and rigor is essential. Leadership also influences procurement strategy. Selecting partners based solely on lowest price may reduce upfront cost but increase execution risk. Leaders who evaluate long-term capability over short-term savings often achieve better financial outcomes. Trust-based partnerships reduce dispute risk. Dispute risk directly impacts cost. Leadership presence on site matters. When leaders remain disconnected from field reality, they rely solely on reports. Reports may not capture nuance. Site visits reveal context. Conversations with field supervisors reveal friction. Leadership visibility signals seriousness about cost discipline. Remote leadership increases risk of misinterpretation. Another powerful influence is risk appetite. Some organizations pursue aggressive growth strategies. They accept higher uncertainty for higher potential return. Others adopt conservative approaches. Neither strategy is inherently wrong. But risk appetite must align with financial capacity. If an organization accepts high-risk projects without adequate contingency or capital buffer, exposure becomes dangerous. Leadership maturity involves matching ambition with resilience. Crisis management capability also defines financial outcome. When unexpected events occur, leaders must respond calmly. Clear communication. Rapid scenario evaluation. Transparent stakeholder engagement. Uncontrolled emotional response destabilizes teams. Stability under pressure protects budgets. Another hidden leadership factor is turnover. Frequent changes in project leadership disrupt continuity. New leaders require time to understand context. During transition, control may weaken. Institutional knowledge may be lost. Stable leadership fosters consistency. Consistency strengthens cost discipline. Ethical leadership is equally important. Intentional underestimation to secure approval creates future overrun. Manipulating numbers to satisfy expectations undermines trust. Ethical transparency may be uncomfortable in the short term, but it protects long-term credibility and financial stability. Finally, leadership sets tone for learning. After project completion, some organizations conduct superficial reviews. Others conduct deep post-project analysis. What assumptions failed? What risks materialized? What early warnings were missed? What structural improvements are needed? Continuous improvement reduces recurrence of overruns. Without learning, mistakes repeat. Leadership determines whether financial systems are tools or formalities. Leadership determines whether risk management is active or symbolic. Leadership determines whether culture promotes honesty or concealment. In construction, concrete and steel form the visible structure. But leadership behavior forms the invisible structure that holds financial integrity together. In the next chapter, we will explore one of the most financially destructive forces in construction: change orders and scope creep. Because while leadership shapes response, uncontrolled scope expansion reshapes the entire cost landscape. Chapter 10: Change orders and scope creep. Few forces in construction are as financially destructive as uncontrolled change. Change is not inherently negative. In fact, change is often necessary. Design evolves. Client priorities shift. Regulations update. Market conditions demand adaptation. But when change is not managed with discipline, it becomes scope creep. And scope creep is one of the primary drivers of cost overruns worldwide. To understand scope creep, we must first define scope clearly. Scope represents the total agreed deliverables of a project. Every drawing, every specification, every system, every finish, every performance requirement. When a project begins, this scope forms the baseline for cost and schedule. The budget is calculated based on this baseline. The schedule is structured around this baseline. The procurement plan aligns with this baseline. When scope changes, the baseline shifts. And when the baseline shifts, cost shifts. The first driver of scope creep is incomplete early definition. If the project begins without detailed clarity, assumptions fill the gaps. Assumptions may underestimate complexity. As design matures, previously undefined elements become specified. These additions appear as change orders. But in reality, they were missing clarity from the beginning. The second driver is client indecision. Clients sometimes refine vision during execution. They may upgrade finishes, add features, change layouts, modify system capacities. Each modification may seem minor, but collectively, they alter cost dramatically. A small aesthetic upgrade across hundreds of units multiplies into significant expense. Another source of change arises from regulatory intervention. Local authorities may require additional compliance measures, fire protection upgrades, accessibility adjustments, environmental mitigation. When regulations evolve during execution, cost impact follows. Even when regulations remain constant, interpretation can shift. An inspector's requirement may differ from early assumption. Disputes over compliance generate delay and additional cost. Unforeseen conditions are another major change trigger. Hidden utilities, unexpected soil composition, structural inconsistencies in renovation projects. Discovery of such conditions requires redesign. Redesign requires labor. Redesign requires new materials. Redesign requires time. And time equals money. One of the most dangerous patterns in change management is informal instruction. A site supervisor receives verbal direction. Work proceeds without formal change documentation. Weeks later, pricing discussion begins. Memory differs. Interpretation differs. Conflict emerges. Formal change processes exist to prevent this. Every change should be documented. Scope defined. Cost estimated. Schedule impact evaluated. Approval obtained before execution. But in high-pressure environments, teams sometimes proceed without formal approval to avoid delay. This decision increases financial risk. Another issue is cumulative microchanges. A project may process dozens or hundreds of small change orders. Individually, each may appear manageable. But cumulative effect becomes substantial. Small cost additions compound. Small schedule adjustments accumulate. Tracking cumulative exposure is essential. Professional project control systems maintain change logs. They quantify approved changes. They track pending changes. They estimate probable changes. Without centralized tracking, exposure becomes fragmented and underestimated. Contract type influences change impact. In lump sum contracts, contractors assume defined scope for fixed price. Changes trigger formal adjustments. In cost-plus contracts, owner bears more risk of scope expansion. In unit price contracts, quantities drive cost. Understanding contractual structure is critical to predicting financial effect of change. Change orders also disrupt workflow. When work must stop for redesign, productivity declines. When partially completed areas require rework, labor hours increase. Rework is often more expensive than initial work because access becomes more constrained. Materials may need removal and disposal. Disruption spreads beyond direct cost of change. It impacts schedule stability. Schedule instability increases overhead cost. Prolonged project duration increases site management expense. Security. Insurance. Temporary facilities. Administrative support. All continue accumulating while schedule extends. Change orders also influence morale. Field teams may become frustrated by repeated redesign. Frustration reduces efficiency. Reduced efficiency increases labor cost. Subcontractors may demand additional compensation for disruption. Disruption pricing is often higher than base contract rates. Another financial impact of change is procurement inefficiency. If materials were purchased based on original design, late modifications may render them obsolete. Replacement materials must be purchased at current market price. Obsolete inventory may not be recoverable. Procurement cycles restart. Lag times extend. Expedited shipping increases cost. Acceleration to recover lost time increases premium labor expense. Scope creep often originates from ambition. Desire for perfection. Desire for competitive differentiation. Desire to respond to stakeholder input. Ambition without financial recalibration creates imbalance. Each change must be evaluated not only for technical feasibility but also for financial sustainability. Disciplined change governance includes impact assessment. Direct cost. Indirect cost. Schedule impact. Risk impact. Cash flow impact. Cumulative exposure. Only when full impact is visible can informed decisions be made. Another hidden dimension is negotiation dynamics. Change orders often become points of conflict between owners and contractors. Disagreement over pricing methodology. Disagreement over entitlement. Dispute resolution consumes time and legal cost. Litigation is one of the most expensive forms of project inefficiency. Strong documentation reduces dispute risk. Transparency reduces escalation. The most financially stable projects treat change as structured process, not emotional reaction. They recognize that change is inevitable. But they require evaluation before commitment. They update forecasts immediately. They communicate cumulative effect to stakeholders continuously. They avoid surprise. Because surprise is what destabilizes confidence. One critical question must always be asked. Does this change increase value proportionally to its cost? If yes, and funding is available, it may be justified. If not, it may represent avoidable overrun. Ultimately, scope discipline protects budget integrity. Every addition must be balanced against capacity. Every modification must be weighed against contingency. When discipline erodes, cost control erodes. Change is powerful. But unmanaged change is financially explosive. In the next chapter, we will explore disputes, claims, and litigation. The final escalation stage when mismanaged change and misaligned expectations transform financial variance into legal conflict. Because once projects enter adversarial mode, costs expand far beyond original overrun. Chapter 11: Claims, Disputes, and Legal Escalation. When communication breaks down, when trust erodes, and when financial pressure intensifies, construction projects enter their most expensive phase. Conflict. Disputes are not sudden explosions. They are slow-burning tensions. They begin with small disagreements. A rejected change order. A delayed payment certificate. A disputed interpretation of specification. A schedule extension request denied. At first, these appear manageable. But when unresolved issues accumulate, positions harden. Documentation becomes weaponized. And cooperation declines. Construction is a collaborative process by necessity. Multiple parties must coordinate constantly. Owner, architect, engineer, general contractor, subcontractors, suppliers, consultants, finances. When collaboration weakens, efficiency collapses. And once disputes begin, financial impact accelerates rapidly. The first financial consequence of dispute is distraction. Project managers shift focus from execution to defense. Emails increase. Meetings multiply. Legal advisors become involved. Time that should be spent improving productivity is spent preparing claims. The second consequence is defensive documentation behavior. Instead of solving problems quickly, teams begin protecting themselves. Every instruction is formalized. Every conversation is confirmed in writing. Every delay is recorded for potential claim. While documentation is essential, excessive defensive posture slows decision-making. Slow decisions delay progress. Delay increases cost. Claims often originate from entitlement disagreements. For example, a contractor encounters unforeseen ground conditions. They request additional compensation. The owner may argue the condition was foreseeable. The contractor may argue it was not. The contract language becomes central. Interpretation varies. Financial exposure becomes uncertain. This uncertainty affects forecasting. It affects cash flow. It affects executive reporting. Another frequent dispute source is schedule delay responsibility. If a project falls behind schedule, determining cause becomes critical. Was delay due to design revision? Was it due to contractor productivity? Was it due to late material delivery? Delay analysis methodologies such as critical path method are used to assess responsibility. But delay analysis itself is complex and often contested. Competing experts may produce conflicting conclusions. Legal cost rises. While experts debate responsibility, schedule continues to slip. Prolongation cost accumulates. Prolongation cost includes site overhead, extended supervision, extended equipment rental, extended temporary utilities, security, insurance, administrative staff. Every additional month multiplies expense. Another escalation stage is formal claim submission. A claim typically includes narrative justification, supporting documentation, cost breakdown, schedule impact analysis, legal references. Preparation of such documentation consumes significant time. If claims become frequent, project administration cost increases substantially. Mediation and arbitration are common dispute resolution methods. They aim to avoid litigation. But even these processes require preparation, representation, and expense. If disputes proceed to court, financial impact increases dramatically. Legal fees escalate. Expert witness fees accumulate. Resolution timelines extend into years. Cash flow remains uncertain during litigation. Meanwhile, reputational damage may affect future business opportunities. Subcontractor disputes introduce additional complexity. If a subcontractor submits a claim against the main contractor, and the main contractor submits a related claim against the owner, coordination becomes layered. Pass-through claims require alignment of strategy. Misalignment increases risk of unrecoverable cost. Disputes also damage morale. When relationships become adversarial, collaboration declines. Field teams become cautious. Innovation declines. Trust disappears. And once trust is gone, efficiency rarely returns. Financially, dispute environments often lead to inflated behavior. Parties may exaggerate positions to create negotiation leverage. Initial claims may be higher than realistic expectation. Counterclaims may follow. This inflation increases tension. Settlement negotiations become prolonged. Extended negotiation prolongs uncertainty. Uncertainty affects investor confidence. Investor concern affects financing terms. Financing cost increases. Thus, dispute impact spreads beyond immediate project boundary. Another hidden cost of dispute is opportunity loss. Senior leadership time is finite. When executives spend months resolving one problematic project, other opportunities receive less attention. Growth slows. Strategic initiatives are delayed. Organizational focus narrows. Prevention is always less expensive than resolution. Clear contracts reduce ambiguity. Well-defined scope reduces interpretation conflict. Structured change management reduces surprise. Transparent communication reduces suspicion. Early dispute resolution mechanisms prevent escalation. Many successful projects implement dispute review boards. Neutral experts monitor progress during execution. When disagreements arise, board review occurs quickly. Early neutral evaluation often prevents full litigation. Collaborative contracting models such as integrated project delivery reduce adversarial positioning. When risk and reward are shared, incentives align. Aligned incentives reduce dispute frequency. Another critical factor is payment discipline. Delayed payment is one of the fastest ways to trigger conflict. Subcontractors depend on predictable cash flow. If payments are delayed, tension increases. Financial stress spreads through supply chain. Strong financial management reduces payment disputes. Claims are sometimes strategic. In competitive markets with thin margins, contractors may rely on claims to restore profitability. If initial bid margins were too low, claims become survival mechanism. This structural issue originates earlier in project lifecycle. Aggressive bidding culture increases later conflict probability. Ultimately, litigation is the most expensive version of misalignment. It transforms technical disagreement into legal confrontation. Legal confrontation consumes time, money, and reputation. And even when resolved, relationships rarely recover fully. Projects that avoid dispute do not do so by accident. They prioritize clarity. They prioritize communication. They prioritize early intervention. They treat emerging conflict as signal, not threat. Because once financial variance transforms into legal escalation, recovery becomes extremely difficult. The financial damage is no longer limited to cost overrun. It expands into legal cost, extended overhead, reputational harm, and strategic distraction. In the final chapter, we will step back and examine the complete system. We will connect all drivers, estimation error, market volatility, productivity drift, risk mismanagement, weak financial control, leadership failure, scope creep, and dispute escalation. And we will define what truly differentiates projects that collapse from those that remain resilient. Chapter 12: the blueprint for budget control and financial resilience. After examining every major driver of cost overruns, estimation flaws, market volatility, productivity friction, unmanaged risk, weak financial controls, leadership behavior, scope creep, and legal escalation, one truth becomes clear. Construction projects do not go over budget by accident. They go over budget through systems failure. Not one failure, but interconnected failures. And if overruns are systemic, then prevention must also be systemic. Financial resilience is not built at the end of a project. It is designed from the beginning. The first pillar of budget control is realistic estimation. Not optimistic estimation. Not politically adjusted estimation. Realistic estimation. This means incorporating uncertainty ranges. It means stress testing assumptions. It means using historical performance data honestly. It means separating ambition from arithmetic. When early numbers are grounded in evidence, future shock is reduced. The second pillar is structured risk pricing. Every uncertainty must be identified, quantified, assign probability, assign financial impact. Contingency must reflect actual exposure, not cosmetic comfort. Contingency is not excess. It is protection. Reducing contingency without reducing risk is financial self-deception. The third pillar is disciplined scope definition. Projects that rush into execution without detailed design clarity create vulnerability. Time invested in design coordination reduces downstream rework. Every hour spent resolving ambiguity early saves multiple hours later. Clarity reduces change. Reduced change protects budget. The fourth pillar is procurement strategy alignment. Long lead items must be identified early. Supplier capacity must be evaluated. Price volatility must be assessed. Strategic purchasing can lock in stability when markets fluctuate. But procurement decisions must balance cost, cash flow, and flexibility. The fifth pillar is productivity monitoring. Execution is dynamic. Productivity must be measured continuously, not assumed. Field reporting must be timely. Variance must be analyzed quickly. Small deviations must be corrected before they expand. The sixth pillar is financial visibility. Real-time cost tracking. Frequent forecasting. Granular cost codes. Earned value measurement. Cash flow planning. Forecast confidence communication. Financial transparency creates agility. Agility prevents escalation. The seventh pillar is leadership discipline. Leaders must encourage honesty. They must respond early. They must align incentives with long-term performance. They must balance ambition with realism. Culture determines whether systems function effectively. Without disciplined leadership, even advanced financial tools become ineffective. The eighth pillar is structured change management. Every change must be evaluated fully before approval. Direct cost. Indirect cost. Schedule impact. Cumulative exposure. Decision-makers must see total effect, not isolated price tags. Scope discipline preserves stability. The ninth pillar is collaborative conflict prevention. Clear contracts. Transparent communication. Early dispute resolution. Prompt payment. Aligned incentives. When collaboration remains intact, efficiency remains high. When adversarial posture emerges, cost accelerates. The 10th pillar is continuous learning. Post-project analysis is not optional. Organizations that systematically review outcomes refine future assumptions. They improve estimation accuracy. They improve risk modeling. They improve procurement timing. They strengthen leadership training. Learning converts experience into advantage. Financial resilience also requires capital strength. Organizations must maintain adequate reserves. Projects involve uncertainty. Adequate liquidity absorbs temporary shock. Thin capitalization magnifies stress. Stress increases reactive decisions. Reactive decisions increase cost. Stakeholder communication is another protective factor. Investors, clients, finances, partners. Transparent updates build trust. Trust allows flexibility when challenges arise. Surprise erodes confidence. Eroded confidence tightens funding conditions. Tight funding increases financial strain. Technology integration strengthens control. Modern construction management systems allow predictive analytics, trend forecasting, automated alerts, data visualization. But technology must support discipline, not replace it. Human judgment remains central. The final and most important element is mindset. Budget control is not about restricting progress. It is about protecting sustainability. It is about ensuring that ambition does not outrun capacity. It is about balancing vision with viability. Construction is inherently complex. Uncertainty cannot be eliminated. But it can be managed. Cost overruns are not inevitable. They are symptoms. Symptoms of misaligned assumptions. Symptoms of delayed visibility. Symptoms of unmanaged change. Symptoms of leadership hesitation. Symptoms of fragmented accountability. When systems align, estimation, risk, procurement, productivity, finance, leadership, culture, resilience emerges. Projects still encounter challenges. Markets still fluctuate. Weather still disrupts. Design still evolves. But financially resilient projects absorb impact without collapse. They adjust without panic. They correct without crisis. They complete without catastrophe. If there is one overarching lesson from every overrun in history, it is this. Early realism is cheaper than late correction. Every honest conversation at project initiation prevents a difficult conversation at project completion. Every disciplined decision during planning reduces emergency action during execution. Every transparent forecast protects long-term credibility. Construction builds physical structures. But financial discipline builds institutional strength. And in the end, the projects that succeed are not those that avoid challenge. They are those that anticipate it, prepare for it, monitor it, and respond to it before it compounds. That is the blueprint for budget control. That is how professionals prevent financial disaster. And that is why construction projects go over budget, and how they don't have to. Conclusion. The real cost of ignoring the warning signs. If you've made it this far, you now understand something most people never see. Construction projects do not collapse because of one dramatic mistake. They collapse because small signals are ignored. Because optimism replaces analysis. Because ambition outruns discipline. Because early warnings feel uncomfortable. And because discomfort is easier to delay than to confront. But here is the truth. The real cost of a budget overrun is not just money. It is trust. Investor trust. Client trust. Team trust. Reputation built over years can weaken in a single uncontrolled project. And once credibility is damaged, recovery is slow. This is why professionals think differently. They don't just ask, "Can we build this?" They ask, "Can we build this responsibly?" They don't just celebrate low bids. They examine assumptions. They don't hide variance. They investigate it. They understand that realism is not pessimism. It is protection. If you are a project manager, a developer, an engineer, a contractor, or a student entering this industry, remember this. Budget control is not about limiting growth. It is about sustaining growth. It is about building structures that stand, and organizations that endure. The strongest companies in construction are not the ones that never face problems. They are the ones that respond early. They are the ones that measure honestly. They are the ones that treat risk as a constant companion, not a distant threat. And now you have the blueprint. You understand estimation risk, market volatility, productivity drift, financial visibility, leadership discipline, scope control, conflict prevention. These are not abstract concepts. They are daily decisions. And every decision compounds. Just like cost overruns compound. Here is the question that matters most. On your next project, will you wait for the overrun to appear on the financial report? Or will you recognize the signal before it becomes a crisis? Because prevention always feels slow. Correction always feels expensive. If this video gave you value, here is what I encourage you to do next. Pause for a moment. Think about one current or upcoming project in your life. Identify one assumption that may be too optimistic. One risk that has not been fully priced. One early warning that deserves attention. And act on it. Not tomorrow. Not next quarter. Now. That single action could save millions. If you want deeper breakdowns on construction strategy, risk management, project finance, and leadership psychology in high-stakes industries, make sure you subscribe. This channel is built for professionals who want clarity, not hype. If this masterclass helped you, share it with someone managing a complex project. A colleague. A partner. A team member. Because awareness spreads resilience. And resilience protects capital. Leave a comment below. What do you believe is the number one cause of cost overruns? Estimation? Scope change? Leadership? Market volatility? I read the comments, and your insight might shape the next deep dive episode. In our next series, we'll explore how mega projects worth billions either succeed against impossible odds, or become cautionary tales studied for decades. Until then, remember. Concrete cracks under pressure. Budgets collapse under denial. But disciplined systems withstand both. Build boldly. Plan realistically. Lead responsibly. And never ignore the early signals. I'll see you in the next masterclass.